Okay, so I think we let us start our class again. I hope that you have a great weekend. Did you take a look at the lecture over the weekend? Good. Okay. You hear me well, right? Everybody hear me well? Okay. All right. So let me actually review what we did last time. Last time we looked at neural network a little bit, just to engage you into deep neural network, and we actually talk about how neural network work look like. What remains is that we haven't talked about how to actually determine the correct neural network, right? For our purposes to get one. So what we can yeah, this is actually not stable. Oh, okay. Okay, so we look at the learning problem, right? Supervised learning problem in particular. That's what we are interested in. What is this here? So wrong. Okay, so we look at the supervised learning problem. Recall, this is the network, right? Remember, it's a continuous composition of alpha transformations and a nonlinear transformation through the activation function sigma, right? And then alpha transformation, and then activation function, and so on and so forth, right? On the way to the L layers. So that's what we looked at last time. And W, right? The alpha transformation that we define is there, right? AI for the I layers, right? When it see the output of the previous layer, it actually multiply by the weight matrix and then add with the bias vector BI. So that's how the alpha transformation look like. And then of course, right, as we can see, each of the set, we haven't talked about how to determine WB, right? But you see that for each set of WIBI, we have a new network, right? And the collection of all of them, we call the hypothesis space. And in particular, this is the hypothesis space generated by neural network, right? L layer neural network. And the space itself, like I mentioned last time, is a very complicated space, unusual space to work with. In particular, it does not have a linear structures, right? Like the usual vector space. It's not even closed or convex in general. So what we assume, right? At least this is actually one of the, you know, kind of very mild conditions, right? We assume that the function that we don't know, which is g, we assume that in L2, that is in square integrable, right? That's a mathematical term, but you thinking about g as a velocity, right? I think we hopefully the math student here, did they take any physics? Yeah, but about at least high school, right? Thinking about g as v squared is velocity, right? Thinking about the integral is a sum. So you're thinking about this as sum of all the velocity of each particle in your system. That's the kinetic energy, right? So that's one way to think about L2. In fact, that originally what L2 designed for, right? The space whose kinetic energies or finite energies, right? So you see that the kinetic energy of the whole system, right? The summation of all kinetic energy v squared is less than infinity. So it's actually it's come from the actual physics, right? Problem that we engineer problem we work. That's why mathematicians came up with, right, with this space. It's not just for pure mathematical interest, right? Just from the motivation from the application. All right. So if we assume, so this is a very mild condition, very, not much condition at all on the object interest, which we call G there. Then the natural formulation is to find a new network that is actually closest as possible, right? Very natural, right? There's a zillion of neural network there. Which one is the best? It's very natural to say, okay, I want to find a network that is closest, right, to my unknown function G. And in the particular in a particular norm there, right? A square norm there. This is called the loss function, right? By the way, that's called typically, let me actually write out here. This is known as the loss functions. In the, there's many names, right? This can, many people call this a loss function. And in more traditional optimization, this is called objective functions. Your objective, right? Or C is your sometimes cost. Cost and loss is the same, right? Cost and loss is kind of similar. Okay, so that's what we looked at last time. Okay, so let me actually put in a more generic style. That's for neural network. Let me. You already have this, right? You already have this. The first chapter or the introductions. I'm gonna go through to set out the problem for you. Using the neural network as a motivation, right? I could go to the this chapter 1 way from the beginning, but then it's so abstract, right? Doing this, we remove some abstract. We can see actually some of the application there. Now let me actually back to our we generalize the formulation a little bit so that we can know, right? This is not the only machine learning problem that we are interested in. In general, this is a much broader activation machine learning problem that I'm gonna show you. Okay. But before doing that, let me do one more thing, right? One more thing. As you notice here, right? In order to solve this optimization problem in general, you see that? I need to know G. See that? We don't know G. But if we want to solve this minimization problem, clearly, clearly f is a function of G, right? If you're thinking about, even forget about the integral, right? Forget about integral. If I want to just simply take derivative and set, the log function to 0, f, equal to G, which is actually not useful, right? Because G we don't know. So we don't know G. This formulation is just instructional for us to put down the formulations. But in practice, right? So this is observations. We're going to put down a few remark. So first, we don't know G. Right? And the question is that how do we evaluate, right? How do we evaluate the log functions? Right, without right knowing in G. Okay, so that's our first challenge. For our first challenge. So in practice, right? In practice, we don't know G, but we have we typically have a peak, right? So a peak. So basically, you just a peak of a peak of V of G through its values at endpoints. So typically, this is what we get. We get xi, right? And then we have gxi. So this is, remember that we are talking about supervised learning right now to make things simple and easy, more intuitive. I from 1 to n. So we don't have G, but we know, right? We do measurement, for example, from measurement, for example, right? For example, from observations or measurement. Of course, right? If we don't know anything about G, there's no hope. This is actually a meaningful, or at least the minimum condition that we should have, right? If you say that, how about if I don't have any evaluation of G at all, then there's no hope to do anything, right? But at least we know something about G, right? Either from observation or from measurements. Oh, by the way, Qinghao, I moved to Taipei over the weekend, so I moved to Gangnam. Gangnam or Gangnam? Is it the huh? Nangan? Yeah, Nangan. Yes, is the yeah, Nangan station, because I live at the Courtyard Marriott there, at the right there under the station. So it's much more convenient, much closer. Or measurements. Okay, so this is actually not too bad of the condition, right? So the question, right? The question is not the questions, right? Now the question is, of course, still, does we replace the risk minimization problem? Risk minimization. By the way, this is also risk minimization. I'm sorry. So introduce risk minimization problem. So let me actually copy this. So this is also known as a risk minimization problem, by the way. I'll copy, I'm gonna put down here. So we're gonna replace this risk minimization problem by the so-called empirical, by the empirical risk minimization problem. So empirical risk minimization, this is quite popular, ERM. ERM, empirical risk minimization problem. So our problem now is just instead of, we still minimization with respect over the WIBI, right? And I from 1 to L. But we don't have the integral. What we have is typically this, right? This is empirical risk minimization 1 over M. Actually, let me do this. Take you for each, let me write, I'm sorry, same thing, but I just want to write more constructive way, right? So we have G of xi, that's what we have measurement for. And then of course, you can evaluate your function on neural network at xi, and then you square them up, right? And then this is the error, right? Or the misfit between your neural network and the actual data. So you sum over all the error, and then you take the average, right? So there's a reason why we need to take the average later. We're gonna talk about that later. But for now, just, the average, we want to minimize the average error, right? Over all the points that we've seen about G. So this is known as the empirical risk minimization problem. Empirical because it's not a theoretical. It's ERM here. Okay, so we have an empirical risk minimization problem, right? So this is, I think, I mean, what I should have done, right, is actually to do this first, introduce neural network first, and then lead to here, and then talk about optimization theory. But it's okay, right? We can always do the other way around, right? We learn optimization here. This is where we're going to use optimization theory, right? And then the most popular approach, right? The most popular approach to solve ERM is by gradient descent, right? If I call, if we set, if we define, data, so big data vectors, right, or matrix, if you wish. This is the collection of all, WI, BI. So you put on the weight and biases into one single. You concatenate them into one single big vectors, right? So then we can, and this we just simply call it a J, right? J. Then the empirical, then the ERM reads that we minimize J as a function of theta. That's a function of theta, right? And this is theta in whatever the space that the theta is, right? So we can then the empirical risk minimization problem now become, abstractly just minimization of J, the loss function or the risk. So we want to minimize the risk, right? So that's also very, very, or to minimize the loss. So very intuitive reason why people call that way. All right, so read. And, we just run, right? We just run, if we need, right? We need the gradient, right? We need the gradient of J with the back to theta in order to run, right? In order to run the gradient descent algorithm. Okay, so how to compute, the key question is that how to compute. How to compute the gradient of J at any theta efficiently. And the answer, right? The answer is the answers. This is the questions. And then one of the answer is to use backpropagation. So the first thing we're going to do today is backpropagation. What is backpropagation? Right? And you're going to see nothing more, backpropagation is nothing more than chain rule, right? We learn chain rule from high school, at least in Asia, right? The high school in chain rule is a chain rule. So nothing more than chain rule, just a different name. And you're going to see why we call it, people call it backpropagation in a second. This is also, right? And if you look at my paper, I show that actually it's nothing more than an adjoint method. In fact, that's what I'd like to think is better, right? For constraint, adjoint is much more generic term and much better in that sense mathematically. But that is it, right? Backpropagation. Any question before we actually jump into backpropagation? So I just provide you, put down a problem setting and lead us to, the need for the computation of a gradient of the loss of functions, right? And we don't need to, as you can see, why should I do backpropagation? That you're going to see later. Backpropagation is the one of the most, perhaps the most efficient way to do so, especially when you have multiple variables. Okay, sounds good, everybody. Can I, any question before I jump into the backpropagation slide? Yes, please. Yeah, that's right. It's, yeah, and as I'm going to show you, it's actually chain rule, nothing, right? So just high school, but advanced high school in terms that you need to order. It's just preparation. It's just a rearrange of chain rule to make your computation efficient. That's it, right? So actually, let me just write it that way. To you can see there's no mysterious here. Right? You know, when you serve preparation, no mystery. It's just an intelligent way to order, right? To order the chain rule. To compute the gradient efficiently. That's it. Nothing more, nothing less. That's all I want you, right? The first lecture today, or I don't know how long it's gonna take, because I really want you to understand it. It's very easy. It's just the key is this, right? The box, you know, the take-home message today, at least for the first hour, is this. Any other questions? Before we actually go into the chain rule, we shouldn't. I shouldn't go. It's so funny, right? Because I go from all the way from America to here just teach you chain rule, which you already learned in high school, right? And you see, actually, you know, something need to see at once in your life. Okay, no, not this one. We're back to the second lecture that I sent you a long time ago. Okay, so this is back thing, right? Remember that this is the neural network. Okay, so and this is what we've seen before. The implementation, we're gonna go to the backpropagation. Okay, so you see that this session is backpropagation, which we didn't go through. You already have this slide before. Okay, so this is we already seen this before, right? Just notationally, and we already talking about this. We're gonna go to here. Okay, so I'm sorry, we a little bit of chain notation, but does not matter, right? So F or J doesn't matter, right? The key is that theta. Where did I put theta? Yeah, theta we already defined, right? Just a collection of all weight and biases. So in order to compute this gradient vectors in gradient descent, remember, right? We do gradient descent. We need this. I should back here. Let me write this. Oh no. Remember that the gradient descent require here theta I plus 1 is equal to theta I, right, minus delta gradient of J, right, at theta I. Okay, that's a gradient descent. So we need the gradient. So the gradient vectors is a vector, right? We need partial derivative clearly. That's where I just rewrote, right? It's just notation. Don't worry about that, right? You understand what I did, what I just wrote previously, 1 second ago. And I want to show you, you know, how to implement, which is very easy, right? It's unnecessary. So we need this. We need all these, right? dj with the theta 0 on the way to theta d. Again, 0 or d doesn't matter. It's just a collection of all, right, weight and biases. Okay, so this is again, I just make it in the boldface there, right? It's just a efficient way to calculate a gradient in the and chain rule. You see that the big thing there is chain rule. Okay, so let's review high school. If we have a composition, which is easy, right? Then the derivative with respect to actually, right? F is composition of F and G. This is what we have. There's nothing mysterious about chain rule. We already showed that. We can also prove it, right? Go back and then prove yourself using limit, right? You can show that easy. Okay, so this is back to our neural networks. What you see is here, right? Remember that I need to calculate the derivative of J with respect to theta. L is a layer, right? L is a layer. So this is the home vectors. I want to take the derivative of my loss function with the weight and biases on the L layers, right? One way to do this is this. Let me call this YL on these Y, right? Are the output from each layer. Remember that Y. Let's say YL is nothing more than sigma of WL, right? And then the output from the previous layers is YL minus 1. And then plus the VL, right? So whatever the output from the previous layer become the input for the next layer, right? So this is what you've seen before. I just wrote this way. So you see that in order to calculate the derivative of J or the loss function with respect to the theta L, record theta L is WL and BL together, right? So theta L. So theta L is just the vector, right? Of by concatenating WL and BL. By thinking about, you can roll out on the columns of the weight matrix, right? By column, and put them together, and then put also the bias, right, into a big vector. That is theta L. Is that good, everybody? Conceptually, theta L, how it look like, right? Good. Any question? This is important. It's easy, but it's important that you get it. Okay, if there are no question, then we continue. So it's just chain rule right there. You see that? In order to actually go into layer L, right? Remember that output is on the way. Let me go back here for you to see the picture a little bit. See this output? The loss function is the F here, right? Involve F. So in order to take the derivative of the loss function which involved here, right, with respect to the L layers, remember this is the Home-Bunsen compositions. I simply go by chain rule, right? If I want to go back here, I just take the derivative with respect to output of this, right? And then take the derivative of the output of this in terms of output of this, right? And so on and so forth, right? Just chain rule on the way. So here. So this is nothing more, right? Then taking the derivative of the last layer with respect to the output of the last layer, right? And then take the derivative of the output of last layer with respect to the output of the L, with respect to the layer before the last layer, right? Because YL minus 1 is the input. Y capital L minus 1 is the input of the Y capital L, right? So so this is the first dj with respect to YL, and then dyl with respect to YL minus 1, right? And then the derivative of YL minus 1 with respect to YL minus 2, and so on and so forth. You go on away until you hit the layer that you are interested in, right? So this is, you take, so this from here to here, this is dj, right? dy, right? That's a dj dyl. So this is, you see that I put the parenthesis there. This is dj to what dyl. Right? And but that's not what we want. We want to take the derivative with respect to theta L. So then I need to multiply with dyl with derivative of dyl with respect to theta L. Everybody see that? That's a chain rule. Okay? So now that's a chain rule, then now you see that very clear. You see that everything is now, the process is now clear, right? This is the box that I want you to see. In other words, if we want to compute the derivative of the log function with respect to theta L, right? All I need is actually dj with respect to yl, right? Which is this one term here, right? And I multiply with dyl with d theta L, right? So you already see, right? This is, and then now, right? Now what is dj with respect to dyl, right? So this one you know. How do I compute dj with respect to dyl? So dj with respect to yl is nothing more than dj with respect to l plus 1, the previous layer. Remember that information go from here to here, right? And now you are at the last layer, right? If you want to calculate the derivative with respect to here, you have to go through, right, the chain rule back. So in order for me to actually calculate the derivative of j with respect to yl, I have to go through the yl plus 1 first, right? Because this is a function of this. And then I multiply with the yl plus 1 over yl, right? So you see, right? You see the beauty, that this is where the back propagation is. When I calculate the derivative with respect to yl of the later layer, I keep it, right, in the memory because I need it for the upstream, right? I calculate the derivative with respect to the output of the outstream, right? At this layer, I have to keep it because I need it, right? I'm gonna need this, right? You see that I need this for what? Let me see if I tell you where do I need this. This actually needs 2 places. Of course, you can see clearly, right? This is needed for me to compute the derivative with respect to yl, chain rule. But one more thing where I need it. Where is it? If I use this formula, right? If I use this formula, right? If I use this formula, I need it actually when I calculate the derivative with respect to the weight and biases of the I plus 1 layer. This I plus 1 layer, right? I need to calculate the dj with respect to dyl plus 1, and then dyl plus 1 with d theta l plus 1. So you see that I need 2 places. This is for gradient, that's sent. But this one for just bookkeeping, right? You need this, the same term, for calculate the true gradient that you are looking for. But it also is help you to compute the gradient of the previous layer. You see that? This is the previous, L is the previous layer. This is the current layer, right? So you need the same thing. You need the same box here for the derivative with respect to your layers weights, right? But you also need to calculate, you also need that for calculate the derivative with respect to the layer of the, with respect to the parameters, right, weight and biases of the previous layers because of the chain rule. Everybody see that? Is it clear? The chain rule. Any question? Yeah. Hmm? Hmm? Oh, yeah, vector, right? Because it's output. Yeah. Say it again. Oh, yeah. You can think it's, that's of course matrices, right? But for the sake, that's very good, right? For the sake of understanding, you can think it's about just a number right now, right? But if it's a vectors, then this of course a matrix, right? It's of course it's a matrix, of course, right? It depends on how you order your vectors, right? This is a row vector, column vectors, right? If you're thinking about this column vector, then this matrix needs to be in front of here because this is a vectors, right? But if you think about this is just a row vector, then row vector times a matrix, then you get back the row vectors. So depend on how you look at it, right? But just simple chain rule mathematics. You're right. If it's in general, it's a matrix, and in fact, that is what the case, right? That's very good. This is also called matrix here, right? White, right? Depend on how many neurons. As soon as you have more than one neuron, then Y become a vectors, right? As long as, of course, this is only a vectors, right? So this is also itself is a matrix. Okay, everybody, good? Any other question? Yes. Good. Uh-huh. Because we need this gradient for the previous layer, because we also need the gradient with respect to the weight and biases, with respect to the weight and biases of the previous layer. Because remember that the gradient vector, right, have everything. Let me see. This gradient vectors contain the gradient with respect to the weight and biases of the L layer of the L minus 1, L minus 2, on the way to little l, and on the way to the first layer. So everything there, right? So you have to compute the gradient with respect to the weight and biases of each layer and put them into this vector or your gradient descent. That's a very good question. Everybody see that? So we need all of them in order to do gradient descent. Unless you said, okay, I want to fix the this layer. I don't want to change it. In fact, there's a method as well, right? The two popular methods is called the support vector machine and random. No, it's not random. Forgot. It's a max something machine, right? Basically, you take random value for the weight and biases of, you have only two layers or many layers, right? You take the random weight and biases for all previous layer. You don't only optimize the last layer, right? So then you only need the gradient with respect to the last layer. A support vector machine, you actually know the weight and biases for the previous layer. But anyway, this is just connections, right? But whatever you want to change, right? Then you need the derivative with respect to that. Any other questions? Yes, we need both. We need this, and we need this. And in fact, we need everybody to put in the vectors, right? To run the gradient descent. Is it good? Okay, so you see that you just keep track. If you just remember that if you keep this in memory, you can calculate these two, right? So the way we're gonna compute the derivative, right, is to go backward. That's why I call back propagation. You propagate backward, right? When you evaluate the neural network, you evaluate from the left to the right, because that's how the conversation works, right? Chain rule, on the other hand, say that, oh no, if you want to calculate the derivative, you need to go from the right to the left, right? That's called back propagation, because you go backwards to compute. Okay, so actually let's do an illustration for you to see more on the graphically how it looked like. This is a single layer. This is a single layer, right? A very simple layer here. The J, which is a log function. Remember that Y is a given output. Remember, Y hat is G. Think about G. Y hat is G. In our notation a couple of minutes ago, G values, right? J, Y is actually F, right? So this is F minus G, J, right? So this is what we just wrote in the generic setting right now, right? So the log function is a function of the output of the network and the data, right? Okay, so we're gonna calculate first DJ with respect to the output with respect to the output of the new network, the last layer here, right? And then we actually pass that information to the next layer, right? We need that. We not only need this for evaluating the gradient of the J itself, right? Because in order to do this, you need this, but you also need to compute, right? DJ with respect to the data here, right? So because it's a chain rule. So you need to pass that information. And then that is not only, remember, right? This not only needed for computing the gradient with respect to the weight and biases at the current layer, but we also need it for the previous layer as well. In this case, the previous layer is the input layer, right? Then you see that the chain rule, if you also want to change X during optimization, you do need this. Right? If you don't want to change X, then you stop here. This is one hidden layer, so easy. There's no need to do backpropagation, right? But if you really want to see, how your output vary with respect to the input, you still need that, right? But thinking about, this is another layer. We're gonna move to the more layer now, right? This is the simplest one, no backpropagation at all, unless you want to calculate the derivative with respect to X, then you do need that backpropagation, pass information backward. You see that, right? Now, this is more generic. You see that, right? So we take the derivative of J with respect to Y. We need it because we pass our information all the way. We need that by chain rule, right? For calculating the derivative with respect to weight of biases for this layer, right? But also for the next layer as well, the previous layer. Okay, let's do by hand. Maybe we're gonna do this in. Let's do a little bit. Okay, simplest case, doing by hand for us to see it, right? So Y, you see that Y, the weight is here, right? This is the weight for the input layer. So H is here, right? So you see that X multiplied by, okay, that's good. Need to stop very soon. Oh, because we do maximum, I shouldn't do maximum thing here. So, right, so this is the output of this layer. H is a vector output of this layer, right? So weight times X is here. And then this output, it becomes the input for this layers, right? This layer, we should remove bias for simplicity, right? Set it bias to 0 for simplicity. So then you multiply by V, which is the weight matrix here, by the output, and then and then evaluate by the sigmoid functions, right? And this is your output. And our output is just scalar, okay? But this is vectors. H is vectors, so X is also vectors. Okay, and then sigma here is a sigmoid function. Okay, we're gonna use a sigmoid function. We have 5%. We're gonna need to charge soon, which I think we should have enough. Okay, and you see that all the dimension is here. W is from 2 to 3, and V is from 3 to 1. Dimension, everything is work well, right? So you see, we define it here. Okay, now we just even take a very seamless case. We take the X values, vectors is 5, 3, and Y hat, the data, the observation G, right, is 1. Okay, so the W we also know, V we are supposed that we also know, and actually that's not the restriction. Why is that? Why can I suppose that I know W and V currently? Why can I do so? Without loss of generality, I can assume that I know the weight and bias right now, or the weight of all layers now. Why is that? Why is that? You need to understand that, because otherwise it does not make sense for us to move forward. Why? Of course, act the input we know, and output the measurement we know. And what I also assume is that W and V are known without loss of generality. Why is that? Why? You need to answer this question, okay? I'm waiting. I'm not answer for you. And it's very easy. I let you look at here. Why can I assume that W and V known currently without loss of generality? Yeah, initialization, but actually more generic. What you said is correct, but I wanted something more generic. Yes. Let me zoom in like this for you to see. Zoom in. So that the answer is clear. Yes, please. No, that's not, I don't know the optimal W and V. I just currently assume that I know some value for W and V, right? But that is not a big assumption. In fact, it's not a problem at all. It's legal to assume. We are doing legal stuff. We can assume W, V values for us to move forward. Why is that? By just looking at this. You have 1 minute to answer my question. You are very close. Actually, you are, huh? Is what? That's correct. We know, right? Because in order to run, very good, thank you. Okay, so this, in order to run gradient descent, right, iteratively, theta I minus 1 is currently we know, right? What we don't know is the gradient, because if I know the gradient, then I can have an update for theta, and I do it again and again. So theta at this current iteration, I know, right? But without knowing that iteration, I cannot take derivative, right? You see clearly also here. We compute the derivative at the current iterations, which we already know. So theta I minus 1 is already known, right? So that's why, and remember that W and V, right? In our case, theta here is W and V, right? So without generality, right? If I'm at the I minus 1 station, I know W and V. Everybody see that? Very good. So it's legal to assume what W and V, and then I just pick randomly. But in practice, it should automatically figure out itself at each iteration. Everybody see that? Okay, let's take 10 minutes break, and we need to charge, and then we continue by hand for the back propagation. Okay, see you in 10 minutes. Okay, so good, right? So the derivative of the sigmoid function is itself 1 minus sigma. Simple calculation show that. Easy, right? To show that. So so dy with respect to dv1, right? Is is what? Is remember that y, right? Y is the what is it here? Okay, y itself the sigmoid, right? This is sigmoid. Y is sigmoid. So sigmoid times 1 minus sigmoid. This is derivative, right? And of course, that in order to calculate derivative, you need the chain rule here, right? D, right? Derivative with respect to sigmoid, and then the derivative of sigmoid with respect to V1, right? Derivative with respect to V1 and H1, which is here. Everybody see that? Chain rule. Same thing for dy dv2, and then dy dv3. Any question? Yeah. Because y is equal to sigmoid, and the derivative of a sigmoid is this. Chain rule. What's that? B plus H. Oh, you mean V transpose H? No, this is chain rule, right? In order to calculate the derivative of y, which is sigmoid, y is sigmoid, derivative of sigmoid with respect to V1, And I need to go through the derivative of sigma with respect to this thing first. And then that thing with respect to V1. I need to take the derivative of sigma with its argument first. And then the derivative of its argument with respect to each of these. But the derivative of sigma with its argument is this. Do it. Just do substitution and you see. This is sigma prime times the derivative of the argument of the sigma with respect to V1. Check. Okay, so this is sigmoid is a function of V1, right? Let me do it this here way, right? So in order to calculate, and this is y, right? dy with respect to the V1, and now this is V1 H1 plus dot 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 dot, right? So this is actually the argument of the sigmoid, right? So in order to do dy with respect to the V1, I'm gonna do the sigmoid with respect to the x first. The x, the V1. Do you agree? Chain rule. The sigma dx, which is here. The sigma dx is sigma 1 minus sigma prime. Dx, the V1 is H1. X with respect to V1 is H1. There. See that? Okay, so same thing for V2 and V3. Everybody see that? Mm-hmm. More? Oh, the white, the white is actually a previous one, right? The the log function, this is 0.25669. That's the log function. I'm sorry, this is where is it? Let me actually go back here one more step. Okay, so this is the y. The output 0.903, which is the y. The output here. Which is y, which or the value of sigmoid for or the output of the output layer. Next. Actually, I'm sorry, I don't wonder because your question completely, I'm sorry. Okay. Values that have this y times 1 minus y. Oh, y is this, right? Remember, that's the output. This y is the 0.509, 0.59. We just have, we already have it. And if that is your question, then the answer for me would be very easy because that's why the output of the output layer. I mean, if he understood you correctly. Okay, so because why? Because you see that in order for me to calculate the derivative of the loss function, this is a loss function with respect to the v, right? Of course, I need to take derivative of j with respect to the output of the output layer first, and then I need to take the derivative of the output of output layer with respect to v, right? So that's what we trying to do now. We try to take derivative of the output output layer with respect to v. Then we multiply by dj dy. That give me the gradient with respect to the v. Right? And then I also need the derivative with respect to w, because these combine, right? W and v combines is my theta. It's good? Okay, okay. Yeah, I'm sorry, I still don't understand your question. I'm really sorry. Yeah, you see that I do substitution now, right? Because this is what I need for the gradient, dj dv1, dj dv2, and I already have this. And I just show you how to do this. I just use chain rule here, right? I calculate, and this is y value. Remember, this is y. Okay, so we check and then this is what? This is h1, h2, x3, which is there. You see that we remember them because we need them. We need them there, right? We need them in this case, the output. You see that? When you do evaluation forward, these are values when you evaluate forward, right? For evaluate the network, you keep them, you don't throw them away because you need them now. See that? Because on the way back, you need them. That's the back probation, right? Just remember that we need them, so we save them. Okay, so do substitutions on the values in there, and then you get the, and dj dy you already know, right? dj dy, this is the derivative of the loss function, right, with respect to the output of the output layer, which we already have here, right? And this is output of the output layer, right? Okay. Any questions? Okay. Don't hesitate to ask me a question, okay? It's just, I'm sorry, if I understand, I can answer you as much as I can, but if I don't understand, I of course cannot answer. But we can always talk. So you see that when I have the derivative, I put it there. Okay, so you see that this is the value of the weight, and this is the derivative of the loss function with respect to that weight. That's how our notation, right? This is the output. This is the derivative of the loss function with respect to the output. So I know the weight, I know the derivative, right? This step allow me to compute the derivative. Now I should move more back. I'm gonna move more in down upstream. I'm gonna move upstream. Question? No. Okay, so then let us move upstream. So we need to calculate the derivative of J with respect to the output of the next layer, right? This is that we remember that we already deal with this layer and then with this way. I need to calculate the derivative with respect to the output of the hidden layer, right? And then I multiply by the derivative of the hidden layer with respect to each of the W chain rule again, right? So first I need dj/dh, which is the output of the hidden layer. And again, the chain rule here, dj, dy, dy/dh. Remember, that's why I need to keep these, right? I save these. So what I already have this. We already have that, which is here, right? -169. What we need is the dy, the h. But then dy, dh, by chain rule or back propagation, we can calculate them easily, right? Here. We already have it, right? We already have the dy, what is that? dy, dh, actually. Do we have dy, dh? We would see the same thing, actually. Let me look at here. We actually skip it quickly, right? But you see that the same thing. This is dy dv 1, right? But if I also want to compute dy with respect to the h1, I would have exactly the same, but then what do I have here? v1. So v1, v2, v3 is dy dh1, dy dh2, dy dh3, right? So that's why we put that in memory. This is just, bookkeeping. If I already have them, which I should, right? If I already have them, I just do substitution. But it's using y minus times y minus y, and times v1. You see that v1? Where's v1? Oh yeah, that there, right? I'm sorry, h. Sorry, not v, h, right? Remember that because I'm sorry. This is the wrong slide. We are at this slide. Wrong slide. That's what that point we already done. So this is dj dy. We already have this value previously. Y minus times 1 minus y, and this is, remember, that's the v1. V1 we already have it, right? This is v1, v2, v3. So that allows us to calculate this, right? This is this. So you see that this actually we already have. We just reuse it to calculate here. But we just showed out you right the explicit thing, but we shouldn't recalculate that. Okay, so now I have that, right? Now I just need to calculate the weight, right? Now this is the weight, W11, W12, and so on and so forth, right? So in order to calculate dj, this here is what? What is here equal to? This equal to this. What is this? Circle. dj with respect to the W11, right? dj, the W11 is equal to dj, the H1, the W11, right? And dj, the H1, we just calculate. We already have it, right? We already have it. So I just simply replace, right? And the W11, so this is dj with the H1, which I just calculate from the previous. dj dh1 here, the value here, derivative of the log function with respect to the output of the first layer, the output of the first neuron of the first layer. Where is that? Okay, here. What is this here? What is it here? Why the H1 with respect to the W11 have this form? Why is that? Yeah, remember that H1 is the output, which is sigmoid, right? So this is the derivative of sigmoid, and then the derivative of a sigmoid with respect to W11, right? So so W11 would be multiplied by X1, of course, right? So this is exactly X1. You see that? 5. Okay, and you do the same. You do the same for all. This is just chain rule, basically, right? But you notice that a lot of information reuse. That's what we're trying to do here. Information reuse, because things, this, right, is reuse, because we calculate, we need this, we just reuse now. Okay, so we calculate the rest, right? We calculate everything for the rest in the same way. There's a note there, right? The gradient to the weights connecting H2, which is here, is larger in magnitude than the others. It's okay. It just happened to be like that. Okay, so then and of course, we know the gradient is the sensitivity, right? So that's gonna, the largest gradient gonna actually change most. So the weight and biases gonna change most in the iterations. Okay. Okay. So if you want to implementation, this is how you implement. If you look at the implementation right there, right? I let you actually do it. Okay. So look, this is that, right? Grad out. This is the sigmoid, right? You see that sigmoid times 1 minus sigmoid times whatever the thing that we need, right? Depends on the derivative with respect to W or H. We can have differently. But the very simple implementation of back propagations is just simply this is forward and then backward. Okay, so at least what I want to show you is at least this is two-layer network. Okay, I let you experience, but it's actually this is exactly what we just show. But the only thing is that we save information, saving. Okay, so let me see. Not much, but yeah. So this is just the program for you to calculate. Okay, everybody, just what is the key message that we just go through, right? If what we show that if you really want to do by hand, this is what you do. But remember that the key is that the information reused. The key is actually this slide. The key is actually this slide that I put a lot of. The key is this slide, right? You can always do this by chain rule whenever I want to compute the derivative. But that is not an efficient way. All right, the efficient way is to notice information actually reuse. The information from the previous layers is needed to compute the information for the next layers, right? So we reuse them, we don't recompute them. When you calculate up to this point, right, and when you calculate up to this point, you don't remove, right? For example, right, if I want to say, oh, derivative of j with respect to theta L minus L plus 1, this is what I need, and then I just throw everybody away, right? Because if you throw it away, then that means this need to be recomputed. We don't. We save it so that we immediately can calculate the derivative with respect to YL. And then, of course, you need this YL with respect to theta, and you should multiply with that, right? Multiply with this. You get the derivative with respect to theta L at that layers, right? And then this one, right? This one is going to be needed for what? This one going to need it for what? dj dyl going to be needed for what? I can draw them away. Right? After I calculate dj d theta l, I'm good. I can throw everything away. I don't need it. But what I'm saying is that this is needed. Why? Why is that? Can you tell me? The partial shape with and theta of what? Of what? L plus 1 we already done. L minus 1, right? That's correct. Because you see that? dj of the L plus 1 is needed for dj dyl. And therefore, dj dyl going to need for, dj dyl minus 1, right? So we save it. So then we don't have to go through that chain rule. Not back propagations. You don't have to go through the chain rule again and again, right? Thing that you need to compute the gradient for the current layer going to be needed for the, the upstream layer immediate upstream layer. And thing that you need, then compute with the upstream layer, you're gonna be needed for the next layer. See that? I pass information step by step back in time. So that's why back propagations. Okay, but the good thing is that you never need to implement that. Good thing, because it's already there, right? By automatic differentiation behind the scene. You never need to implement. This is just I want to show you that if you want to do by hand to fill it, or if for 2-layer, if you want to implement it. I'm sorry, it's a little bit easy, right? This is how one way to implement. One way to do Python, right? To implement the back propagations. But the good thing is that when you use any platform like TensorFlow, JAX, PyTorch, it's already done for you. You should call the gradient. But what we show today, you know what behind the scene, right? Why come back propagation and why it the particular way, right? Because of the rearrangement of chain rule. Reuse, information reused. That's important. Information reused. Okay, any question before we move to the next thing? Okay. Yes, please. Why do we need H? H is just a Y, right? The Y. So your question actually, he actually answered in this slide. I'm sorry, the notation is not completely consistent, right? It's not, it's consistent. It's just when you apply for a particular case, right? Because H is Y, the output, right? The output of H is the Y, the output of a current layer. Sigma. So, okay, so do you agree that you need the derivative of J with respect to the output of each layer? And H is the output of that particular layer, right? Let me go here. H1 is the output of that layer or that neuron, of the output of neuron 1. H2 is the output of the second neuron, right? And same. It's good. Just we apply that algorithm for this particular network, and we call it H1, H2, H3. Okay, good question. Okay, if there are no more questions, we're gonna go to one more important topics of gradient. So things seem to be very nice, right? That's it, we done. But in fact, not done yet, right? There's a problem. There's a problem with this so-called gradient vanishing. Gradient vanishing. So let's actually move to the next problem called gradient vanishing problem. So now we know how to do calculation, the gradient, right, by back propagation. That's fine. That's fine. So we're going to look at. I'm going to do in order to demonstrate the gradient vanishing, right? I'm going to look at one neuron for each layer just to demonstrate thing for you, right? But the result is applicable for generic network with many neurons on each layer. But for the sake of simplicity, I'm going to assume that all the layer have one neuron and the bias, you see that's also zero. On zero thing is a bias, right? So, and we're going to consider again sigmoid activation function. In fact, the sigmoid activation function is the problematic guy, right? So sorry again, the notation changed again. This is the log functions, right? Derivative of the log function with respect to the bias, right? The bias of the L layer, right? So how do you do a chain rule, right? If you do chain rule, and of course to demonstrate, I did to show you the chain rule. That's enough to show, because chain rule or back propagation compute the same thing. It's just back propagation is more efficient. So if you do chain rule, this is what you get, right? you said that I need to calculate the derivative, right, for all the previous one, and then on from L, right? In order to get the derivative with respect to the L layers, of course, I need to know the derivative with respect to the on the previous layer, right? L plus 1 to L, chain rule. This is chain rule. This is chain rule. Everybody okay with that? This is the chain rule dy, right? This is the d. This is yeah. So that's one the pi. So the pi of w I, derivative of sigma I from L plus 1 to L, right? This is nothing more than the yeah, this is nothing more. Okay, so remember that sigma I is our yi, right? Yi. So this one is nothing more than dyi minus 1, right? So dyi minus 1, which is the derivative of this yi a sigma I, right? The sigma I is the wi yi minus 1 plus bi, right? So if I want to calculate the dy with respect to dy minus 1, this is nothing more than, of course, right, chain rule, the d of sigma I first, and then with respect to its arguments, and then the derivative of its argument with respect to yi plus 1, which is wi. Everybody see that? So so this is so this is nothing more than the pi of I from L plus 1 L of this product, right? And this, on the other hand, right, this on the other hand, right, is nothing more than equal to d of y L derivative with respect to d of y. And the last guy is what? L. Everybody see that? This product is nothing more than this. So this one, right? This one is nothing more than that. The y of the YL, right? And then remember that I want to calculate, right? I want to calculate dl, the loss function with respect to dBL. Of course, this is nothing more than the loss functions with respect to the dyl, the output of the last layer, dyl dy L, right? And then similarly d y L with respect to d b L. Chain rule. Everybody okay? And this one is this. They're equal to each other's, right? dyl dbl is again. So dyl dbl here. dyl dbl is equal to what? This implies dyl over dbl is equal to what? Remember that only a number, not vectors. Equal to what? The sigma I, right? Where the sigma I is equal to sigma L. The sigma I is equal to sigma I 1 minus sigma I. I put it there. Where? I didn't. Okay, so this is the term, right? Everybody see that? This is DYL with respect to DBL. Okay, so you have everything here. So this is D, I'm going to explain why I have minus later, right? So this is DYL, DBL. That's the last term. This last term. And this guy is the products. YL minus AL because of this. Because of the eraser right here. So we have, I didn't tell you, actually, did I say somewhere? No, the log function that we have is y minus a. Actually, I actually I twist a lot of information here. I'm sorry, I use a lot of new information, new. Let's get back to our notation, right? This is half. This is 1/2. Okay, so if it's 1/2, then of course there. This is y, and this is a L. I'm sorry. Okay, so this is our YL, right? Which is the output of the last layers. I'm sorry. I use when I prepare this slide, I use different notation. Okay, let me actually change this a little bit. Okay, so this the YL here is actually our YL, and this is actually y hat, right? The data, and the log functions is this. Log functions is 1/2 of y hat minus YL, the output layer square. Simple, right? So you see that you see that this. So therefore, the L with respect to the y hat, YL. Y hat is given, right? YL is equal to, of course, right? You do it either way. This is YL minus Y hat. Everybody see that? I mean, I just wrote this in the, negative of Y hat minus YL. It doesn't matter. Everybody see that? So the minus side together, the minus side, I'm sorry for the confusion, the minus side together with this, right? They are nothing more than the L over the YL. This, right? So well, let me rewrite this as well. This is DL DBL is equal to DL with respect to DYL, and then DYL with respect to DY little l, and then DY little l with respect to DBL, right? And remember, right? We just our notation is this: D sigma L is sigma prime, right? But sigma prime itself, remember, the sigma prime itself is sigma 1 minus sigma, right? If you want to expand, but that's that the sigma is just sigma prime. Okay, and we have I have just show here, right? So this, the green circle here, is nothing more than DYL capital L with respect to the little l, right? And this one, dyl, because yl is equal to sigma of wl yl minus 1, right, plus bl. So because of that, this is nothing more. This is nothing more than equal to d sigma l, right? D sigma l. Something happening as well. So this room is not good for us. Unfortunately, we're gonna have to use this room for the next, today and then tomorrow and then on Friday. So everybody, do you see everything? Everybody, right? So this is this term. This is this. The minus sign. Y hat minus YL is this. So that chain rule allow us to see the derivative. Okay. Any question before we move to the next things? Yeah. Say again. Many. Oh yeah. We have many of them. We have many, L, actually L from 1 to L, capital L. Bias. But same thing, right? This is but if you want to replace this with respect to bias here, let's say I do WL here. Actually, that's good. What should be changed? Actually, let's do here. Actually, he asked a question. Give me a chance to ask you now a question, okay? So this is the good professor. That's how you do it. When the student asks you a question, you turn it around, ask back a question, and let the student answer the question instead. I'm just joking. Okay, so if I want to compute, of course, right? It's sufficient. What we claim is that this is sufficient to consider DLDB, DLDBL to consider vanishing problem because the capital L with respect to the WL look almost the same except where to change. In fact, if you actually can do calculation in your mind right now, right? What should I change here in order to calculate DL with respect to DWL based on that? What should I change here? One single change, and I'm done. Cooler. I'm sorry, I just don't. Bias. Mm-hmm. They are fine. Information. Yeah, partial L, partial BL. That's correct. So we have, right? Every layer have bias right now. We actually now we consider generic term, generic situation where you have bias every layer. That's correct. Say it again one more time. We only need to yeah. This one, right? That's not the same way. Minus one. Uh-huh. Oh yeah. If you only calculate derivative with respect to this guy, then the bias will not affect. Yeah. But but we, right? We still need because later on we can remember that now if you move to I, right? Because you need to do the same thing in I here, right? So you see that I depends on what? On these, right? You still need derivative of with respect to this in order to calculate the derivative with respect to BI. Thinking about right? In order to calculate the derivative with respect to BI, I need to calculate the derivative with YI first, right? So we still need this in order to calculate the bias, but the bias of the previous one. You still need this DL DYI minus one whenever you want to calculate the DL DBL minus one, right? In order to calculate DL with BI, I need to calculate DL DYI first, and then chain rule through here. So this is still needed, right? But it's not needed for this I layer. But derivative with this one will be needed for the I minus one layer, the form of the upstream layer. Okay, so it's not that we don't need it, we need it, but for the next layer upstream. Good. Okay, so I still have a question back for you. Okay, don't worry, right? I gave you more time to be break later, and Murphy only stole us 5 minutes. Oh, I already mentioned her. She showed up immediately. I just badmouth you, and you came here. I did. I think I did. Did I? Or did not? I didn't. I'm sorry. I thought I did. Oh, yeah. I need to let the screen stay longer. Okay, so let me change that setting later. Okay, I should be sharing now. Yeah. That's right. I'm sorry. It's when the screen is on sleep, it's automatically stop sharing. I forgot that. But I'm gonna make the sleeping time actually longer, so we will not have that issue again. Okay. Yeah. Thank you. Okay. So when you say when you check it, your responsibility to remind me, right? If it's on off, then remind me to share. But I'm gonna change that after this class. Okay. Okay. So how about this? Think about it, right? Think about this. We're gonna come back to this question. If I want to do DLDWL, what should I change here? That's my question for you. Is that clear, everybody? Good. So I'm gonna see you at 4:10, or a little bit more between 4:10 and 4:15, right? I need to go to the restrooms, and do we have tea or something for the student or whatever? Okay, we got you. Okay, so I see you in 10 minutes. Good. Okay, so we are back in business. Okay, remember the question I have for you before we leave for break is if I want to do DL, DWL, right? Then what should I change? The reason I didn't do that because it's the same thing, and so we don't need to look at that. We have seen actually, on the other hand, this is complementary, right? We look at DL, DW already. This is the first time we see DL, DBL. Okay, can somebody answer my question? If I do DL, DBWL, what should I change there? Sure. Oh, my question again? Oh, I thought it was okay, so maybe I write, maybe I write better. So we look at the DLW on radio, right? How about, can somebody tell me what is DL? Given all the information that we have so far, DL, DWL is equal to what? So that one, you mean the whole thing here? You want me to write the whole thing here? That one, you mean the whole thing? The whole thing, or yes or no? Okay. The whole thing. So what he said is this, right? I write the whole thing, but let us write into the order, okay? We're gonna write into the order. So the sigma L and then pi I from L plus 1 to capital L W I d sigma I, and this is y hat minus y I'm yeah. By the way, I still don't understand why I wrote that way, right? We have minus here. We don't need to, but okay, I have the whole thing, and then what? Anything change, or that's it? I just rewrote the whole thing like you said, you asked me to. What else that I should, or is enough like that? Multiply by y I minus 1 L. Yeah, L minus 1. Any suggestion? Any objection? Like we are in court right now, okay? Any objections? Either you don't agree or you disagree. If you don't agree or you agree. What he said, is that correct or not? Yes or no? Remember, we are talking about chain rule here. Not difficult question. So how many people, raise your hand, how many people, or students, of course, student only. How many of you thinking that what he said is correct? Can you raise your hand? 1, 2, 3, 4, 5. We have more than 5 students. So that means the rest either disagree or not sure. Let me ask you about disagreement first. Any of us actually disagree with what he said? Everybody, this is a class, right? I want to interact with you so that you work instead of going to a class and then don't work and then, okay? So I don't mean to, it's not intimidating or anything at all, right? I just want you to work on the fly, right? To understand and for us to interact. So what he did, what he said is correct, okay? What he said is correct by chain rule. because everything is still the same, right? Everything is still the same. You still need the okay, so to see it here, right? So this one, instead of having this, I'm gonna have DYL, right, with DWL instead of BL, right? But then that means that would mean the sigma L by chain rule times the sigma with respect to YL plus one, which is I'm sorry, WL, which is YL minus one. Very good. That's correct. Thank you. All right, you see that is exactly the same, right? The red term there and this is exactly the same. So we don't need to change anything. Any concern before I move to the next slide? Okay, then we are close to the great and vanishing problem. Okay, the derivative of sigmoid function, by the way, let us plot. Let us plot the sigmoid function so that you can see better. So this is x, this is sigmoid. So the sigmoid function is 0. Let me use different color. This is our sigmoid functions. This is 1. I remember that the sigmoid is equal to 1 over 1 plus e to the negative x. Okay. Okay, so that's we have it. Actually, this is 1/2 here. Let me actually plot it again one more time. Okay, plot my plan one more time for you to see. So this is the middle. Okay, that is sigmoid functions. Let me actually see one. It's sigmoid. How about the sigma, the derivative? The derivative look like this. So the derivative look like this. So this is sigma prime, which is sigma 1 minus sigma. Okay, so the largest values is actually point, right? So the largest value here is 0.25. So the sigmoid value actually less than 1, right? The derivative, the largest, I'm gonna start with the largest values. But let's say we are at the largest values, of course. The largest values, the key points, that is actually less than 1. Of course, everywhere else is actually less than 1, right? So therefore, the absolute values here is equal to, right, this. Okay. So each of these, the largest is 0.25, right? How many of the sigma in here? I'm looking at B1 right now so that we can see things better, right? If this is 1, then this is 1. This is, remember that L plus 2. If this is L plus 1, I'm sorry, L plus 1. So 1, then L would be 1 plus 1 is 2. So here, right? So I'm looking at the on the way from the first layer, right? I'm looking on the way to the first layer. Then how many d sigma here? You have L minus 1, right? You have one more here, so L. So total, right? And each of them is less than 0.25. 0.25 is the largest. So the left-hand side here taking the d sigma alone, right, is less than 2.25 to the power L. Everybody okay with that? Because on these are multiplication, right? This time on this is less than 0.25 L. And let's say you initialize, right? Let's say the so this is the weight and biases. Typically, when you do the training, you initialize by do randomizations, right? And then just pick the easiest case for us to see, right? Let's say the initialization you just draw randomly, then let's say it's approximately 1, just for the demonstration of the, it doesn't matter what it is. It doesn't matter what it is, right? But approximately 1. Then I don't see this, right? Because approximately 1. Otherwise, I have some value here. But that's not the problem. The problem is and then y minus AL, I keep it, right? So you see that the deeper, the key, the problem is here, right? The problem is here. This is very small, especially for large L, right? This is 1/4 to the power L. So the bigger or the deeper network, the gradient of the upstream layer is smaller and smaller and smaller. Everybody see that? The larger the L is, the derivative with respect to the weight, also the weight, right? Because the weight, I'm just, he already answered the question for us. The weight have the same term. I had the same term there. So we have the smaller and smaller gradient as you move upstream, right? You have a good gradient at the on the way to a layer, output layer, but as you move, as you progress or back propagate, you multiply 0.25 to the L, 0.25, I'm sorry, 0.25, 0.25, 0.25, and then when you go all the way to the input layers, right, or the first hidden layers, the gradient is very small, right? I mean, if you can test your computer now, right? This is think about 2.5 here. Let's say 0.0, actually 0.1. Let approximately 0.1. This is 10 to the negative 1, right? Approximately. This is 10 to the negative L. 9 layer or 10 layer, you already have 10 to the negative 10, which is very small. Have 16 layer, 10 to the negative 16 already. Why do I pick 16 layer, by the way? There's a reason. 10 to the negative 16, then I starting having problem. Actually, even before 10 to the negative 16, I have problem. Why is that? Huh? Time? Time. The time to take to do calculation? No. But a good guess. Why do I concern 16? The number 10 to the negative 16 is very special. In terms of computation, let me give you a hint, right? In terms of computation, 10 to the negative 16 is very special. A double precision. That's right. Because all of the laptop or computer, all of them, right? Or most of them, or if not all of them, all of us, our computer is actually double precision. And the machine zero is what? What is the machine zero? Approximately, what is the machine zero? The number where your machine considered to be zero. This is on computation, right? So you see that we don't actually only do math, prove theorem, but we also need to care about in practical as well. So what is a number, a finite number that our computer or our machine actually consider to be zero? What is it? Any of us here have MATLAB on your laptop? Do you have MATLAB there? Any of you can have laptop? I'm sorry, MATLAB? Can you open it? Any of us, by the way, any laptop here have MATLAB? None. Ah, you do. Okay. Can you type in EPS? EPS Oh, okay, okay. No, MATLAB is good enough. You need to open MATLAB first. Oh, I'm sorry. Other program I don't know. Maybe, but MATLAB I know what EPS and the MATLAB show. So you don't have it. It doesn't go. It doesn't show. Or slow. You know, Professor Computer should be to be superb, very, very, very fast. Okay. So if you go into, right, because each language have different notation. The reason is that I know very well because when I was a student I deal with this thing a lot. But if you type EPS in MATLAB or other 10 to the negative 16, right? 10 to the negative 16, approximately 2 point something. I even still remember, right? 2 point something 10 to the negative 16. That's a machine. EPS is an epsilon, right? That stands for epsilon. So that's actually machine zero for our computer, right? So the reason I raise it up here because you see that even with 16 layer, you already hit machine zero. So the gradient is essentially zero, right? And what is the problem if the gradient is zero? What is the problem? What is the problem if the gradient is zero? Let me actually open this and let you show it to you. Huh. I'm asking you, what problem would the gradient go to zero? Why is it so beautiful? It's zero, cool. Why? What is the problem? That's correct. That's very good. Right? Let me. That's good. Very good. Here, it's not stop. It's not stop. So you say almost correctly. It does not stop. You can say stop as well. So if the gradient is zero, right? This is a vectors, right? So the update depend on each component here. If one of the component of the gradient is zero, then the theta or the variable for that component does not change, right? Because it's zero here. So the next iteration is still the same. So you spend time doing gradient descent, but it does not move anywhere, right? The main point, remember that I show you when we study gradient descent, every time we get better, we prove conversion, right? And one of the conditions for the gradient is to be non-zero, right? So we go downhill, we change every time. But if gradient is zero, then we don't change, right? So then it's saturated, right? It stopped changing. So if you run more, it's just a waste of time. It doesn't change, right? So gradient vanishing is very critical because we're wasting our time, right? But then it does not change. That's the first problem, right? The second problem also this tell us the analysis that we do here. Of course, the closer to the input layer, the closer to zero or vanishing problem that we have. But the downstream is okay, right? The consequence is this. When you do training, only the latter layers actually changing, update. You cannot learn. You cannot learn the layers, input layer or close to input layer. The layer upstream is harder to train to learn, right? But the layer downstream is easier to learn because it changed. The gradient is non-zero and changing, right? But this one, the gradient for the weight and biases upstream is so small, only 16 layer. If you Google a little bit, the larger the network can have million, right? Can have a billion weight and biases and can have huge, L can be very large. Right? But ChatGPT, you can check ChatGPT, how many layers in the new network there, right? So then we run into problem immediately. It does not change, right? So of course, there must be a way to avoid it, right? That's why ChatGPT can learn. But this is the problem. If you don't do anything, we have problem. Okay? The network does not learn by gradient descent. Okay? Very simple. Everybody see that, right? Of course, you see here. Okay. This is for generic. This is for first layer. For L layer, this is how it look like. For L layer, this is L minus L, right? Little capital L minus little L plus one. So this could be very small as well. So when you say small, it changes very slowly, right? So it's very hard to train. So you need to run a lot of gradient descent or a lot of epochs, right, in order to change this, which that's not efficient. Okay. Okay, I'm going to show you one way to fix this problem. Okay. Any question before I show you the way how to fix that? No. Okay, if no question, then we're going to show how to fix, right? One way I'm going to show you ResNet, right? Residual neural network. The residual neural network designed to do many other things, but one of the things that it helps ResNet is actually useful for many reasons, or the derivation of ResNet is that motivation behind it is actually not quite solving gradient vanishing problem, right? It do something else. Okay, everybody, you see that I change notation, right? This is y instead. Our previous notation we have y here, right? But we switch to a right now. I'm sorry. Okay. It's just that in my paper I use a instead of y. But in the other slide I do y because y for us y is output more natural, right? I'm sorry about that. But this is the original one. The ResNet, what do? You do a very special thing here. Without this is the standard feed-forward neural network. If you also add, right, you see that the output of the L layer is equal to the output of the previous layer, L minus one layer, plus activation function, R5 transformation, nonlinear activation function. Now add with the output of the previous layer. This is ResNet. They call it residual, right? It's residual because you still left something over, right? Residual neural network. Okay, and if you look at this, it's very, very similar to what we learned from numerical analysis. What is it? Which Euler? They have two Euler, backward Euler or forward Euler. Which one? Or you you don't distinguish between backward Euler and forward Euler? Which one is this? Backward or forward Euler? So what he said is this is actually nothing more than Euler. Okay, so let me actually write out because you may not have, you may say this word differently, right? Euler, Swiss mathematician, very famous, right? Do a lot of things for us. So one of his methods is this forward Euler or backward Euler? Which one? Okay, so let me actually write it. Okay, so this is forward Euler. So backward Euler is more implicit. This is explicit method. See that? Explicit. Because the output, you don't see that L, right? The L, the YL is actually not here. I'm sorry, this is L minus one. So you see that the right hand side is completely determined by the previous layer, L minus one. Or thinking about the current time step, completely determined by the previous time step, right? So layer is actually very similar to time step. Time, right? L plus one time, and then L time, and then L plus one time. I'm sorry, L minus one, and then L plus one. So this is a forward Euler discretization with time step equal to 1. Okay, so if you think about that way, then you immediately can make connection with ODEs. Right? When you take the limit, if you put delta t here, and you take the limit when delta t go to 0, you're going to have an A prime here, right? You're going to have the y prime equal to this. Then you have neuron ordinary differential equation, right? Neuron ODE is also very famous and very useful. Okay, so if you multiply by delta t and take the limit, then you can have neuron ODE. Okay, but we're not going to talk about that. Just want to make connection for you. The ResNet idea is very simple. Right? We just add what we have before. Of course, if you do that, there's a restriction. What is restriction? So the neural network, not only that is special, but also there's some very special about the ResNet. So far, you see that we do generic, right? This one, each layer, the number of neuron can be different from the others, right? But this one, RedNet, what a restriction for a RedNet. Have to be what? The same, right? Because otherwise the dimension will not match. This is the output of the L layer. This is output L plus one layer. If they don't have the same number of neuron, then the dimension mismatch. We have problem. So the new ResNet, one of the condition is that all the layer have the same number of neurons, right? In order for this to make sense. Okay. Then we continue. We continue. We actually we go through the same exercise again, but now we're going to calculate the derivative of the loss function with respect to BL again. Right? We're going to do the same exercise again. We have the same exercise again, and yeah, I don't know why I put lambda there. Okay, so I'm sorry, but I don't know why I put lambda there. Yeah, because I'm sorry, I remember now. This actually, this is adjoint, right? Adjoint. Forget about that, everybody. I'm sorry. Let me erase that. Let me erase that. Okay. Let me erase this. Forget about this. Actually, I copy from one of my actually right here. I think I copy from this the lecture notes here, Drayden. Let me make sure. If you look at the notes, lecture notes, I think you're gonna see the lambda L there, I think. Oh yeah. Actually, you're gonna see lambda there. Oh yeah. So the lambda actually the notation actually from here I copy it and paste here, so that's why. But don't worry about that, right? Don't worry about this. Okay, so I DL with respect to the BL. Of course, I missed one term here as well, right? I missed one term here as well, which is the y hat minus YL, right? Or, in our case, it's a hat minus AL. I'm sorry, AL and YL is the same thing. A hat and Y hat is the same thing. Okay, the only change, you see that look exactly the same, except they have one here instead. The only difference from the previous one previously we don't have this one. Now I have one here, right? Thanks to this, we have one here and one here. We have one there. Chain rule, you need to do by yourself, right? Convince yourself. That is correct. Convince yourself. Okay. Now, and this is hat minus AL. Okay, so then we no longer have problem. We have no longer have problem. Everybody see that? See the way I say here? We no longer have problem because remember that previously on the sigma, d sigma is less than 0.25, right? And then you multiply them together. If W is approximately 1, this is going to approximate 1.25. So everybody is now approximately 1. right? We no longer have problem 0.25 to the power L. The only thing that we have 0.25, this one, 0.25 times on these. On these is about 1. Everybody see that? If on the W are approximately 1, then this is at most 0.25, right? And therefore 1 plus 0.25, or this one can be 0 as well, that's fine, right? Because there's 1 still here. So on these term square bracket here, approximately 1. So all the gradient is now well defined. No longer a vanishing problem. Is that good? So that's one way. Of course, again, it's not originally what ResNet is using. But you can, of course, you can say, okay, why should I use the sigmoid function, right? That's one way to use ResNet. The other way is, oh, you should use different activation function, right? Where the derivative, the value of the derivative to be small is there's no such a thing, or very rare. The value of the derivative is small. For example, ELU, exponential linear unit, right? You don't have that problem at all. Okay. Okay. So that actually conclude our today. So today we actually do the really 2 important thing, right? Actually 3. We did the motivations, why we need optimization, right? And then we say, okay, and then the most important method to do optimization is to do gradient descent. Good things that we only learn how to come gradient descent. But in order to do gradient descent, we need to know the gradient. How do we compute the gradient in the neural network? Chain rule, right? And backpropagation is just a intelligent way, or just rearrange the chain rule to compute it more efficiently, right? We don't need to recompute. That's the second method that I want you to know. Then gradient descent, right, or backpropagations could be problematic if you use sigmoid functions, right? Because it's actually zero vanishing, right? And of course, if you use the other function like ReLU, you may also have problem, because ReLU, half of ReLU is derivative is 1, half is actually 0. If you be at the 0, right? Somehow your weight and bias is such that the derivative is 0, then you have problem with vanishing gradient itself for ReLU. ReLU by far the most popular, right? But even that, this is ReLU, doesn't matter. If this is 0, doesn't matter, because if you use ResNet, no problem, right? So you either to change the activation function or you use ResNet, but there are many other ways to do the gradient vanishings. There's also gradient exploding problem as well, right? There's 2 problems, gradient vanishing, which is more critical. The gradient exploding because of accumulation of error. You do, right? Because you do stochastic gradient descent. We talk about that later, right? So our goal for the next 2 days is to go through, some probability theory, and then go to stochastic gradient descent and prove that stochastic gradient descent actually converge. We only prove the gradient descent, the standard deterministic one, converges, right? We only need to look at the stochastic gradient descent and prove that converge, and we accomplish our goal, right? To cover really, most fundamental problem with deep learning. Okay. Any question before we leave for the day?